So let's get started. Thank you for joining me. Today's talk is about how we build Murally. For those that ain't familiar with us, I will show you. We are an online zoomable canvas that people use real time to collaborate on ideas. We are working on iPad, Windows, and web apps, drawing, brainstorming, and stuff like that. So the idea is to talk a little bit how we got up to this point and the lessons that we learned along the way. So let's get started. This is where we are, or a quick glimpse of where we are today. We have 432,000 registered users, 2.5K are concurrent, people are spread over 193 countries. Our average response time is around 60 milliseconds. We serve 10 million requests per day, and we spend around $467 to host all that. So basically, we learned along the way, the hard way, right? One morning, out of the blue, we appear featured on Google Chrome Store, and we went from 300 signups per day to 7,000. We had to do some changes. Hopefully, we were fast enough to keep a good availability time, but still we learned some things. So the first one, so everything that I will show here is the process as we did it, like hey, why don't we try this, why don't we try that, let's keep evolving what we have. So try at home whatever you will see here, and first I'll show you what we will be working with. So this is Murally as is. This is Murally for us. It's the same, but it's just sticky note. We have here an app that it's an HTML5 thing with just one widget, and it's a Node app that just serve that. We will take that from here up to a real-time thing that writes on a database, talks to other clients, and all the optimizations that we've done along the way. So first thing that we learned was that nobody gets it right the first time. So our first idea was like, hey, we're talking about creating this multi-user real-time connected app. Why don't we create a WebSocket environment where the server itself is another node on the network, and we send stuff between clients, and just there is one that saves on the database, but everybody gets updated at the same time. Well, that failed, but failed, like tremendously failed. Like people were seeing stuff that wasn't stored. Store stuff never gets to people, and lots of stuff like, hey, I'm seeing these, but when I refresh the screen, the page, or enter the next day, data was lost. It was bad. I mean, it was really bad. So we said like, hey, what can we do? So we started thinking how we wanted the information to flow. Like, hey, we have one person here, we have a web server, and we have a lot of people connected. In fact, we have murals that have like 50 people real time working on a brainstorming session or a voting session or something like that. So we had that, and we make our decisions based on, we want to guarantee that everything that you're doing gets stored, and then we will figure out how we dispatch the messaging to the rest of the connected clients. So in my mind, the design was like, hey, we will always make the information flow one way. That's why the arrow, well, it goes the other way, but that's why we draw like this arrow, and we say like, okay, we have a client, we will post to our web server, the web server will store. Once we acknowledge that everything has been saved, we'll dispatch to the rest of the clients. So we have like this continuum of information where the client writes one way and receive information the other way, but it's not sending and receiving through the same channel. That sounds more complex than it is. In fact, I'll show you right now. Let's do this the other way. So just to give you an example, this is what our mural will look like on the database. We're using MongoDB. It's really simple. We have an ID that it's the mural ID, and then we have a dictionary of widgets where we have like X and Y, where on space it is, height and width, the background color, and I think I should have put the text, but all of them will say like, hello, I'm a sticky note. So this is what we are going to store on the database. The first thing that we thought, it's like, why this format? Like, if you think, why would you, I mean, widgets tend to be an array. Like, you would think, why don't you put an array? The answer is because when we were designing all these, we thought like, hey, if we go and update a widget, if I want to update a widget directly, on Mongo, I can issue an update that says like update widget dot the ID dot the property, and go like in-depth update. So I don't have to bring the stuff back up, check the position in the array, and then issue an update. That's a problem that Mongo has, that is arrays are sorted, and if you want to update one element inside the array, you have to know the index. That was really, really complex for a real-time environment, so that's why we stick with this. So that being said, I'll go to the console, Mongo HTML5DevConf 2014. I think I should have put another name, but that's fine. And I will create our first widget, which is what our first mural, which is what we just seen. I'm just saying, because I did some tests, update and absert, like rewrite the mural with the ID number 1, which has widgets and everything that we've seen. So now we have the database. The next step will be to actually go ahead and serve this back to the client. So the first thing that I'll do here is like I'll create the function. This function will connect to MongoDB and return me a database instance. I need to require here require MongoDB, Mongo client, and that's one of the things. The next one will be this one. This is pretty simple. We declare a route. It takes the mural ID as a parameter. We look up on the database for that particular thing, and we send that back to a client. So this is all that we need on our server code. I will go ahead and get rid of this. So if we go back, we have, I'm not running the app, sorry. If we go back, we have an empty mural. Now let's populate that. I'll get rid of this, which is stuff that we have. The first thing that I'll do is I'll map the widget itself that we have to an HTML structure. I create a function that it's called widget template. What it does, it takes one of our widgets and sets CSS properties on the thing, like background, width, and as I said, it will always say, hello, I'm sticking out, but that could be another variable there. So the next thing that I'll do here is this. What it does is we'll grab the jQuery element of the thing and handle the drag and drop and update X and Y based on the mouse movement. That's pretty easy. And the last one will be to fetch the mural. So what I'm doing here is I'm turning that object dictionary into an array of widgets and merging the ID property as part of the widget, so it's easier to deal with. And then I'm appending that back to the board. So here we have this. We are not writing yet, but we are fetching stuff from the database. So this is somehow the way we work. I mean, it works in reality. So the next obvious step for this will be to store actual stuff on the database. So in order to do that, what I'm going to do is I'll handle the drag end event. So when we are done dragging, I'll say like, hey, let's update this guy. What I'm doing here is like posting back to the server an operation. We work with operations, so we create this sort of pipeline where we send stuff and stuff gets converted into MongoDB kind of queries. So what I'm saying here is like update the property X with the X value, which I'm reading from the DOM for the widget ID, and the same for Y. Back on the server side, we'll include another route that will handle the post to the same mural. We send this operation, we grab the mural ID, we have a function that I'll show you to turn those operations into an actual MongoDB update statement, and then I'll fetch the database itself and update and apply the updates. So this is the get values piece of it. What I'm doing is a switch on the operation. If it's an update, we use $set, which means just update this property. Do not rewrite the whole document. And that's pretty much what it does. So I will restart the server in here, go back, I'll move something, stored, works, pretty easy. So when we got to this point where we were storing stuff, we said like, good. I mean, works, it's fine, it's simple. Most of our people understand the way it works. It took like just 10 lines of code to write this. But then we learned, this is when we started learning the hard way. So so we said like, how do we get this connected? How do we make like, the first thought was, hey, why don't we just poll the server every couple of seconds and do an update? That wasn't a great idea either. So the other one was like, hey, there is this thing that is called Pusher. There are plenty of similar things out there. But what it does, it's a WebSocket backbone. It gives you a way of people to connect to a WebSocket channel and send and receive messages, and they give you a server-side API for actually sending messages to those channels without needing to open a WebSocket. When I mentioned before that we try WebSockets, I want to run out of it. I want to say like, hey, we don't want to use these because it's really complex to scale. So if you are familiar with Socket.io or Signalar or those frameworks for do-it-yourself kind of WebSocket backboning, most of them rely on shared memory. So you will use either Redis or another key value store to store the actual server memory across all the nodes. So that's something that I didn't want to get into and was hard to scale. So we said like, hey, let's go with these guys. So to turn this into a real-time connected application, we just need to do some changes on our app. The first one will be here on the index. This relies on, we need the pusher key to connect. So I will put hidden here. So we read that later. On the server, I will change this line to grab the pusher app key from an environment variable, so all of you looking at this won't take pictures of my variables and use for your stuff. So that's one of the things. The other thing that we are going to do, which is really, really simple, and this is how it works in reality, it's like here I will replace this with this. What is he saying is after we do the update, what we are going to do is say for the HTML5DevConf channel, issue an event called operation, and we will just forward whatever comes from the client. So everybody speaks the same language, but we don't dispatch until we don't know that it has been stored properly. So this will send out what we have. I'm forgetting this one, which is important. That is, I need to declare pusher. Pusher is a standard Node.js library. Pusher required. We open up the thing, and now that we have the server-side piece in place, what I'll do is I'll change this this here. So first, I'll instantiate pusher in here. This will read out of our hidden thing where I'm storing the key. Then I will add here, once we are ready and the mural has been loaded, I will add this that will simply listens on HTML5DevConf channel and handles the operation event. And that's pretty much what I will show you right now, because it will need some changes. So
could you say the problem you were trying to solve by adding pusher? You said you're having problems. Was it that it got slow or CPU load? What was the issue?
Why we are using pusher?
What was the problem that you hit that you had to make a change at all?
Yeah, so the thing why we end up using pusher was because we needed to dispatch to the connected clients, and it was really hard to keep up from our side, and it's really hard to scale. So I tried to build my own backbone for WebSockets, where I put an HTTP interface and a WebSocket interface to talk and all that, and it was really too complex to keep up. At some point, I think we'll have to do it ourselves back again, but for now we are good. One thing that it brings back that question is, like, when we are doing this, we are talking with all the connected clients. We are sending them a message, but the protocol that the server is using to send that message is plain old HTTP. It sends an HTTP to an endpoint, and then the clients here will receive the operation through a WebSocket, or long polling, or flash socket, and that was the other one. Because when we did just plain old WebSockets, we found out that customers inside corporate networks didn't have WebSockets access, and devices have crappy WebSocket API. So we said, like, hey, let's go with these guys that have like fallbacks. So this, what it will do now is I'll run the app here. It will store stuff on the database, but it has a problem that we are going to fix right now. That is, if you look at this, every time that I'm moving, I'm getting my own operations back. And that's, I mean, until we figured that out, that was a bad thing. Like, things were changing all the time, and we end up with like infinite loops of ourselves updating something, then receiving the operation, and then trying to update the operations again. This is pretty simple to fix. These guys have they have a property on their connection that it's called the socket ID, which is a unique identifier for your connection. So we are saying, hey, we are sending all these operations out from this client, and then when we send that back to our server, we will say regbody.socketID. This is a parameter that will filter us out from the dispatching, so we don't get our own messages. And now that we have done this, what we will do here is, like, here, instead of doing a console write, we will handle the actual operation. What we will be doing is, like, I left the comment there saying that this is a hack. Since we are using two properties, the way that I'm defining with CSS property I'm going to update is asking if it's X is left, if not is top, because they are the only two things that we're updating. But in reality, we have a dictionary that maps model properties to CSS properties, and it would be easy, but for sake of this demo, I think this is fine. And then what we are doing is we are looking for that widget on the canvas, and then we are changing the CSS property to the value that we received through the server. So I'll restart this guy here. I'll be moving this here, doing some changes. As you can see, nothing happens here, but if I open another connection, I have two. I think that they look the same. Just to make it more evident, we're right. So we have a real-time synchronized connected application that stores stuff on the database and then talks to a client. We have defined what I call on the first thing how the information will flow. We always know that we are writing one way and we are receiving that at the end of the tunnel. So it's not like we are sending and receiving. It's really clean, a clean design where it has a beginning that is an HTTP post, and it has an end that it's WebSocket operation received through a channel. So that was our lesson number 2, which was like, we really need, I mean, when you are building something like this, you really need to sit down and think how the information will flow and what will happen if you want to hook in between, where will you receive stuff, when will you be sending stuff, and all that. So that's our lesson number 2. Lesson number 3 is don't become your own distributed denial of service. Why? So if we go back here, I will maximize these two guys, and we go to the network panel, we will see that every change that we are doing is sending multiple HTTP requests at the same time. I think, yeah, I even kill my own database doing that. That's fun, and it's good because it illustrates the concept here. If that happens in production, I'll be crying like a baby and spending the whole night long wake up trying to fix this. So my first take there was like, hey, we need to find a way to avoid being our own denial of service. Doing some research, I found that there are some guys that wrote a library called AjaxQ with a Q at the end that has the same jQuery Ajax interface that we're using, but they handle the client-side queue. So they guarantee you that each client won't be making more than one HTTP request at the same time. So let's implement that in here. So first thing will be to add that library. Just it's AjaxQ there. And the next thing that we're going to do is change here. So we have something in here that it's another snippet. I will get rid of this now. So we have again X and Y. We are sending the same JSON, and we are defining the name of the queue right there. So it has a parameter for you to say like how many concurrent requests you want. For sake of this demo, I will say just one. So with that change, there is nothing that we need to change on the server. I'll just clean up these and start doing stuff. So I need to be really fast. So they appear one by one. Let's go again. So you will see them in batches because it's local, but it's just one, then the other one, then the other one. We don't do, I mean, if we make the client a little slow, it will work the same way. But that's one way that we have caught our clients, which is really interesting to the numbers that I showed at the beginning. We went from unknown to known. We know that no matter how many concurrent clients we will always have one HTTP request writing for each one of them. So that gives us like the third lesson, that it's don't be your own denial of service, but in reality it means that you turn something that wasn't countable to countable. You just need to monitor how many concurrent users you have, and then you multiply the number of requests that you're allowing on the queue, and then you have simplified how can you prevent traffic. So that was a good lesson, but still we are sending two operations. So we said like, hey, this doesn't make sense, even though we're updating X and Y and there are two properties. The natural flow would be like, hey, why don't we turn this into a batch? So let's go ahead and do that. It is really easy. So here on the client, what we are going to do is to say operation equals an array. So we have this array here. And what I will do is I'll copy this, and I'll do operations dot push this guy. I remove the socket ID from individual payloads. Since we are going to send one payload, we'll include it on the higher, one level higher. So X, Y, and and we'll change this to be operations. We don't need the second request in here. And the good thing in here will be that since we have one request, we'll need to do some change on our post. Instead of generating values out of the plain body, we are going to generate it out of rec.operations from there. And then the next thing will be to change this to its batch version. What it does is grabs all the operations and merge it into one MongoDB update statement. So it's the same set, but now gets fed from multiple operations. And with this being said, the last change that we need to do is on the client. Since now we will be getting more operations, we just rename this back to payload, and we will do payload dot operations dot for each function operation. That's why I use snippets a lot, because it's really hard to type and talk at the same time. Okay, so what it does here is it will grab each one of these operations and apply the same way it was doing before, but now we take and send batches. So let me restart the server. So now every time that I move, if we look at the payload, it will be an array. So X and Y go on the same HTTP request at the same any given time. So this works. I'll show you our second client here. Still working. It's a little bit faster because we don't have to do two things. So we get X and Y at the same time, which is cooler. We can also do more stuff that we do here that is like, but I didn't want to get into details, that it's, we just grab the widget once instead of looking it up many times. We order the operations by widget and then we update widgets on request animation frame, so it works a little bit faster from the client perspective. But for sake of demo, this is fine, but it can be optimized. So good. Right now we went from a disconnected app to an app that writes on the server, broadcasts. We save time by doing a batch. We save time by queuing and guaranteeing that just one client is sending one request at the same time. But it wasn't good enough for us. So we said like, hey, we still need to keep going. And the thing that came to our heads was like, we were about to challenge the power of now, or in other words, eventually consistent, still consistency and still good. So on our case, when we are doing this, I'll show you on the network, which is more clear. Every time that I update one of these guys, I'm sending one HTTP request with 2 operations. What if I could buffer for a little while, like let's say 5 seconds, and then send everything that happened on those 5 seconds to the rest of the client, so we avoid. It's not that we will know how many concurrent HTTP requests we will have per user. We will also know how many concurrent requests we will have per user per unit of time, like let's say 5 seconds. So we know that if we have this many concurrent users and we see their pattern, we will know that they are hitting ourselves every 5 seconds. It's not more than that, not less than that. Well, less if the operations queue is empty. But we said we need to get this fixed, because 5 seconds will be a lot for us sitting here. If I show you the demo, it won't be as cool as it is right now. But for 2 people sitting 500 kilometers away, whatever that is in miles, that's like 5 seconds is nothing. I mean, if they can keep collaborating and working and all that, and the only delay that they have is 5 seconds, in reality we have 2 seconds, but it was too fast for the demo. So we'll change this from here to issuing a request when there are changes to be sent every 5 seconds. So let's go back to our code, and it's not a big change. The first change is operation gets promoted to be something that's living and breathing throughout the app. It's not widget specific. We will keep pushing operations there, but this guy is gone. And we will include here what I call the dispatcher. The dispatcher is a set interval every 5 seconds that will copy whatever is on the operations array blanket and issue the HTTP request every 5 seconds. So if we go back, this doesn't even require us for a server restart. I'll do clean up here, clean up there, and I'll do this, so we get to see the thing. I move, and it moves. It takes a while, but it's good when you are doing all these. So eventually it will get there, but as you can see, we're just sending one set of operations every 5 seconds, and even though it has a delay, a real delay, which we are forcing ourselves to have, it's still good that the person on the other side will get just one I/O operation, which is this WebSocket call with plenty of stuff to update the UI. So it's always a trade-off of how long we make him wait, but there is the networking time that plays a role there, where maybe 5 seconds seems too much, but then switching and getting frames from the WebSocket through the cloud and all that, it's slower than that. So we buffer on the client, and it ends up being faster to update many things at the same time from the perceived user experience. So this is great. We went for, again, we did the whole path. We sorted out our way of working. We went from unknown to known. We went from bunch of operations to a set of operations, and now we are not only controlling how many concurrent requests we have, but also we added a time variable to that. There's still room for improvement. If you take a look at the operation that we are sending in here, I'll clean it up and make a quick demo of what I want to show. Let's wait 5 seconds. So if I open up the HTTP request in there, I should stop stepping on this. We are sending six operations, but we are always updating the same X and Y. Do our customers, our database, or anyone else cares about all those intermediate values on those 5 seconds? Definitely not. So even though we speed up the whole thing in terms of concurrency, users, and all that, we still are spending more on the bandwidth because we're putting together a bunch of operations that we even don't care, because since they are sorted and the MongoDB update is just one SQL MongoDB statement that is a dictionary, it will keep only the last values. We are sending data over the wire, paying for that data, not only here, but for every connected customer, when we don't care about all that. So let's update our thing here to be smarter. So that's what our lesson number 6 is about. Smart clients are better clients. If you, I don't know if you noticed, but until we went from nothing to batches, we did have to change server code because it wasn't the same. But since there until now, we improved lots of things, but still we didn't have to change anything but our client. The server keeps working the same way, but we are saving server money by doing these things. So we will turn our forwarder client to a smart client that it will keep only the last operation for each one of the properties. So first change in here is that operation becomes an object. So now that it is an object here, instead of doing this, what we are going to do is say operations widget ID plus the property name equals this. I think it's faster if I duplicate. So what does it mean? Every time we change the same widget, the same property, we just keep that last one until we send. So let's change the send code. Here we say, well, we will need to blank the operations on our end, and then some changes like this is object keys and then we are sending keys map operations to key. If I forget the return here, it would be a disaster. So we map our dictionary to our original operation payload format, and if we refresh here and here, even though I can be moving this many times, I will always get 2 in this case, because one is X and Y. No matter how many times I move on those 5 seconds, I will always have one pair of operations being sent out. So smart clients are better clients. That's what we say. If we can beforehand simplify what we're sending back to the server, it will represent less bandwidth, less money, and faster communications, because when we were sending all those operations as an array, we had to update the DOM many times. So you can see the transition of the thing moving like clunky. It's better this way. Number 7. So one thing that we were thinking and we ended up doing was, what happens when things take more than those 60 milliseconds that we want to constrain our average response time to be? What we've done is that since the client, the server talk the same language, they all understand operations, what we were doing here is like, you will introduce at this level, before sending, we will queue messages. We use the Microsoft Azure queues, but you can use AWS. I think AWS has a SQS, the queuing service, or any other queue service. We will just queue those operations. For example, when you invite someone to a mural, that's another operation that what it does, it pushes a member to a member object. But it doesn't do that only. It also sends an email. So the email we handle off the HTTP pipeline. What we do is we just enqueue that, we update the database properly, we dispatch that someone has been invited to the rest of the connected clients, but then on the background we are reading that queue, doing changes, and sometimes we are even using the same code, the same trigger events, so we can send notifications to connected clients from a background service. So the fact that we made everybody talk the same language is a way that we, like, hey, we grab this operation, we defer that, and then we process that, and then we push that back to the connected clients, or new operations, or different type of things. But everything that it's not critical for our business in terms of writing the database or letting the rest of the people know that that there were changes, we do it on a background with a queue, and we don't care when it gets done. I mean, if 5 seconds is enough for real time, imagine that 1 or 2 hours for delivering an email would be okay too. Never takes that much, but it could take that much, and it won't affect our overall system performance. And the last thing that I wanted to talk about is, well, these are the drawings for that. We go from, we were used to going from client to server. Now we can go from client to server and to queue, and then go back either to server, backbone, and connected clients. The last and the 8th lesson is like, this is someone that everybody will tell you in every type of talk, from from doing grunt kind of work up to performance, client-side performance, web server performance, whatever. It's like you can improve what you can measure. So before jumping and doing all of these, you should get a hold on what's your reality, because for us, 5 seconds and 1 concurrent connection per client is good. For your case, maybe different. Maybe you can support 2 concurrent connections. Maybe you can wait more than 5 seconds. All those measurements, you have to know them beforehand so you can play. Because if you take what you've learned today on what you've seen and go back to your project and try to copy the same numbers, it might work. I mean, I won't tell you that it won't work, but it's not the reality. You have to know your own reality so you can adjust the variables accordingly. Thank you. I think we have like a minute or two for taking questions. everything that you've seen, including the presentation and the code, it's available on GitHub. There is something cool that I wanted to show you regarding the GitHub thing is that what I did yesterday was I went through the talk, like I rehearsed the talk, and I saved a commit on each one of the individual states. So you have from the initial version to the version that only stores to the database to the version that this is a version that fetch from the database, the version that stores from the database, the version that goes real time, and then updates sent through the queue, batch, dispatcher, smarter clients, and the README and the presentation that you've seen today. It's good because if you wanna tell someone else and show what you've learned, you can just check out the first commit and then move forward. On the repo, you will find the same PDF with the presentation and the link and everything like that. That's my Twitter handle. We can follow up whenever you want. I think that since we are the last until the lunch break, we can do more than 1 minute of questions if you have any. If not, yeah.
What did you use to measure? When you said how do you measure yourself?
Yeah, so that's an interesting one. We use New Relic.
New Relic?
Yeah.
Yeah, we started.
Yeah, we use New Relic. It's good that they have, we use both, right? They have the server version, which is like plug and play with Node, you require that. But then they have the RAM, which is a real user monitoring, because you have to use both, and they make your conclusions out of that, because the RAM, the real user monitoring, will tell you the latency and the real perceived value from your customers. The other one, the one that you put on the server, will tell you, hey, you went really fast in 20 milliseconds. And the truth is, like, there is an overhead, you are missing a CDN and stuff like that. So when you're measuring, keep those measures, like from client side and server side.
How are you dealing with race conditions? So if you have two clients trying to modify the same sticky note at the same exact time.
The last writer wins.
What's that?
The last writer wins.
The last writer wins.
So,
I mean, does that always happen? I mean, if one client is sending it out at the same time, he's not getting the final result, right?
yeah, so when you do the change, you don't do the change. I mean, you don't wait on yourself to do the change, so you will see something. The fact that Mongo locks for doing the update will put on hold on which is the latest version. So we'll lock, send, and then we'll receive yours and update. So what might happen is that you see your thing moving twice, but we test this with like 50 people doing a voting session and a brainstorming, and the number of times that someone was trying to tweak or touch the same thing at the same time was really low. Also, we have feedback saying, and this is the other part of the talk that we didn't talk about, is like we send real-time feedback through the WebSocket saying, hey, I'm touching this kind of thing. That doesn't go through the server. So we do peer-to-peer, we don't care. Always the last writer wins, but we give the user the option to know that, hey, you don't want to touch that because someone else is touching. Yeah?
Would it ever make sense to batch requests that are unrelated, like, not the same database call, for example? Just to, conserve on HTTP requests?
Yes, so we in fact, we do that. Like, we just, everything that changes a widget, we batch that. But if you wanna, I don't know, invite someone or change the mural title or do something else, we just split that up and don't batch things that don't go together.
So we just have like a catch-all API endpoint or something like that that'll just deal with requests?
Yeah, the truth is that we have an endpoint that handles all these operations, and it's like a post to change a mural, and then we turn the operations into one Mongo statement. The good
Right.
thing is that the way it was designed, it works if we batch everything. Like everything that you can imagine, from inviting people, changing titles, updating widgets, everything can go into the same into the same Mongo thing.
Yeah.
We have some smartness in terms of like we don't update stuff that we are deleting. So if you do tuck 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 and then you delete, then we just send the delete and stuff like that. But we do both. From the client's perspective, we try to just batch whatever makes sense to be batched.
Sure.
But our API is ready to handle batches of stuff that is completely unrelated. I mean, related at the mural level.
Right.
We start off the mural, and then everything that goes down that path can be touched from that. Any other questions?
Thank you. Best talk today, man.
Thank you.
Yeah, very nice.
Thank you.